So welcome back for the next topic in chemistry, ionic bonding. So in terms of learning objectives for this particular unit, which should take us about 3 weeks, you're going to have to be able to describe how ions are made or formed, know the charges of the following ions, metal ions of group 1, 2, and 3, the non-metal ions of groups 5, 6, and 7. Periodic table can give you a little hint on that. You'll have to remember the ions formed for silver, copper, iron, lead, and zinc, and also remember for the non-metals, hydrogen, hydroxide, ammonium, carbonate, nitrate, and sulfate. No two ways around it, you just have to remember those. Then, now we have the formula of the ions. You're then going to use those formulae to determine the overall formula of compounds formed when these ions interact. And then look at ionic bonding. We're going to do something called dot cross diagrams and be able to draw them to see what happens to electrons in ionic bonding. Understand that ionic bonding is caused by something called electrostatic attraction. Understand the properties of giant ionic lattices. And finally, know why ionic compounds do not conduct when solid and only when molten or in solution. And when I say conduct, I mean conducting electricity. So ions. So ions are known as charged atoms. They have a positive or negative charge. Okay, so either they lose electrons to become positive or gain electrons to become negative, because electrons are, of course, negative. So a non-metal from group 5 or 7 gains electrons to become a negative anion, and a negative ion then ends with "ide." For example, a chlorine, which loses electrons, becomes the chloride ion. And a metal from groups 1 to 3 loses electrons to become a positive cation. And atoms gain or lose electrons to form ions with unreactive full outer shells. Okay, so what happens is they lose electrons and their outer shell, their valence shell, becomes full, so they're now stable. So ionic bonds form between nonmetals and metals. Okay, one gains electrons, the negative ion. One loses electrons, the positive ion, to become stable. And here's an example here: sodium and chlorine. Okay, so atoms have protons in their nucleus, and it determines what the atom is. They have electrons that orbit in the shells, and they are electrically neutral. Okay, so atoms are electrically neutral, whereas in an ion, the shell structure prefers certain electronic configurations. They lose electrons or gain electrons to become ions. So here we have sodium. It has lost its outer electron to gain a net charge of +1, and you'll notice now it has a full outer shell. And chlorine has gained an electron. Okay, notice there's 7, there's 1 missing here. Now it has gained an electron, so again its full outer shell is, well, it's full, it's stable, it's unreactive, and because it's gained a negative electron, it's now become an anion overall, negative.
In this lesson, we will learn about what ions are and how they are formed. When an atom gains or loses electrons, they develop a charge. Recall that electrons are negatively charged, so the gain or loss of electrons will create a charge. These charged particles are called ions. When an atom loses electrons, they become positively charged. Positively charged ions are called cations. An easy way to remember this is to recall that cats have paws. When an atom gains electrons, they become negatively charged. Negatively charged ions are called anions. Let's look at sodium as an example. Its electronic structure is 2, 8, and 1. It has 1 electron in its valence or outermost shell. When sodium loses this valence electron, it becomes a positively charged sodium ion. This charge is written as a superscript when writing the symbol. When drawing the electronic structure, enclose it in square brackets and write the charge on the top right-hand corner. Now, let's look at oxygen as another example. Its electronic structure is 2 and 6. Therefore, there are 6 electrons in its valence shell. Oxygen gains 2 electrons to form a negatively charged oxide ion. Remember to include the charge when writing the symbol and when drawing the electronic structure. If we look at the electronic structure of these 2 ions, we will see that they have a complete outer shell. We will also see that they have the same electronic structure as that of a noble gas. The sodium ion and the oxide ion have the same electronic structure as a neon atom. How are you feeling about ions? Are you ready to form ions on your own? Let's try. Please pause the lesson and draw the electronic structure of a calcium ion and a chloride ion. The electronic structure of calcium is 2, 8, 8, 2. It loses 2 valence electrons to form a calcium 2+ ion. The electronic structure of chlorine is 2, 8, and 7. It gains an electron to form a chloride ion. These 2 ions have the same electronic structure as an argon atom. Did you get the structures right? And did you remember to specify the charges? What do sodium and magnesium have in common? They are both metals, and metals lose their valence electrons to form cations. Group 1 metals, such as sodium, have 1 valence electron, and they lose this electron to form ions with a +1 charge. Group 2 metals, such as magnesium, have 2 valence electrons, and they lose these electrons to form ions with a 2+ charge. Oxygen and fluorine are both nonmetals. Nonmetals tend to gain electrons to form anions. Oxygen is in group 6 and has 6 valence electrons. It gains 2 electrons to form an ion with a -2 charge. Fluorine is in group 7 and has 7 valence electrons. It gains 1 electron to form an ion with a -1 charge. Group 3 elements, such as aluminum, lose 3 electrons to form ions with a +3 charge. Group 5 elements, such as nitrogen, gain 3 electrons to form ions with a -3 charge. Group 4 elements, such as carbon, tend to form covalent compounds. Stay tuned. In conclusion, an ion is a charged particle formed from either the gain or loss of electrons. A positively charged ion is known as a cation, and a negatively charged ion is known as an anion. The ions formed have the same electronic structure as their nearest noble gas.
So another thing you have to do is write formula for compounds that are formed when ions interact. Okay, so one question you might be asked is that you're given a reaction, but the formula of the chemicals in it are not given, and you're told to balance it. So it might be a word equation. Often you need to make sure you correctly worked out the formula of the ionic chemicals in the reaction, and ionic chemicals include all the compounds made of metals and non-metals used in this course. This includes things like iron oxide, copper carbonate, and calcium sulfate. And I'm going to give you now a step-by-step guide, only 2 steps, and maybe even a little cheat at the end, to work out how to do that. Okay, the first thing you have to do is know your ions. Okay, so all these positive ions and negative ions we see on this table on the left has to be remembered. Okay, you can kind of work some of them out from the periodic table. For example, magnesium is in group 2, so it'll be a +2 ion. But some, like hydroxide and ammonium, you're just going to have to remember. There are certain rules, okay, to remember. So metals always form positive ions, non-metals form negative ions. Only 2 exceptions. Both hydrogen and ammonium, which are non-metals, form positive ions. The charges are written in a superscript above the chemical symbol, and the numbers in the subscript below are the number of atoms or ions. So if we look at carbonate here, then 2 minus is going to be the charge, and 3 is how many oxygen atoms we have in the carbonate ion. The second step is balance those charges. Okay, the ionic compound is going to have an overall charge of 0 because the charges of the anion and the cation will cancel each other out. So you need to balance the charges on chemicals until the charge of the plus ions and the negative ions are the same. Then you don't put any charges in the final formula of your chemical. Sometimes the example below is an example where it's simple, like sodium chloride. So you have one sodium plus ion, one chloride ion. The plus and minus cancel out, so the formula of sodium chloride is going to be NaCl. Simple. Okay, plus and minus cancel out. You notice that the plus and minus aren't even in the final formula. Of course, there can also be harder examples. So when two ions have different charges, you need to balance their numbers to get a total charge of 0. So the example below is known as calcium chloride, and it often comes up as a question because it's made when you react marble chips with hydrochloric acid, which is an important reaction in rates of reaction. So you'll see that the calcium 2 plus, okay, has a charge of 2. The chloride has a charge of 1 minus. Okay, so one calcium ion with a charge of 2 plus and 2 chloride ions each have a charge of 1 minus. So 2 plus minus 1 minus 1 will equal 0. Okay, so the formula of calcium chloride is CaCl2. Okay, because you've got to have 2 chloride ions to balance out the plus 2 charge of the calcium ion. So the final example is something called a polyatomic ion. Okay, polyatomic just means many atoms make the ion. So some ions contain more than one atom inside them. Carbonate, nitrate, sulfate, they're all examples of polyatomic ions. So how do you deal with these? Let's look at the example of calcium carbonate. Okay, so again, you've got calcium 2 plus, and you'll see the carbonate, the overall charge of the whole thing is 2 minus. Okay, so one calcium ion has a charge of plus 2, one carbonate ion has a charge of minus 2. So this just means that 2 minus 2 will equal 0. So calcium carbonate is a formula of CaCO3. Okay, we're going to use lots of examples in class to practice this. So let's just continue on. So a cheat I kind of use is something called the swap and the drop. Okay, so I'm going to use the example here of potassium phosphate. Okay, so what you do, the first thing you do is you write down the ions. Okay, so the example there is we have potassium and phosphate. You then swap the numbers at the top because obviously you're going to write down the ions, so it's going to be 1 plus and 3 minus. Okay, phosphate's 3 minus. So you just swap the numbers around. Okay, so now that becomes K3, and that just becomes phosphate because it's just 1. Okay, you then drop the numbers down to become the subscripts. Okay, so you drop the charges, get rid of the charges completely, and then you drop down the subscripts. And then you reduce down to a common factor, okay, which you don't need to do for this particular example because it's still a 3-to-1 ratio. And you put brackets around the polyatomic ions if you have more than one of them. Okay, so we'll just get rid of those there, don't need that. So the actual formula of potassium phosphate is K3PO3. Okay, so you don't need the brackets because you only got one of the phosphates. Okay, and we're going to practice that again more in class. So the bonding between the ions that we just looked at is called ionic bonding. Now, ionic bonding is a chemical bond that involves the electrostatic attraction between oppositely charged ions. Now, what does electrostatic attraction actually mean? Well, you might learn in physics that positive charges and negative charges are attracted to each other. Okay, that's known as an attraction which is electrostatic. It involves electricity, positive and negative charges. The reason why is because one of the ions has lost one or more electrons, and one of the ions has gained one or more electrons. So if we look at the example of sodium chloride, this example here, the sodium atom has lost an electron and has become overall positive. It's now got a stable outer shell, valence shell. Okay, it's full. And the chlorine atom has gained an electron to become the chloride ion. Okay, so you can see in the second half of the diagram that the positive sodium ion is now attracted to the negatively charged chloride ion. This is known as electrostatic attraction, an ionic bond. So what happens when ionic bonds form? Well, using the example of the sodium and chlorine, the chlorine gets one of the sodium electrons, and the chloride and sodium ions form. Okay, so you can see it here that the electron from the sodium atom is taken by the chloride atom, so the sodium cation forms and a chloride ion, anion forms. The sodium ion and the chloride ion then form an ionic bond as the negative charge is attracted to the positive charge. And we can represent these things in form of a dot cross diagram, where the dot represents the electrons of one atom and the cross represents the electrons of the other atom. In IGCSE, we're at the advantage, you don't have to write all of the electrons out. All you have to do is write out the dots and crosses for the valence electrons. So looking again at the sodium chloride example, the sodium atom gave an electron to the chlorine atom. Okay, and you can see that here by this red dot. The result is that the sodium ion has an electron configuration now of 2,8. It's stable. It's got 8 outer electrons. It's unreactive. And the chloride ion now has a stable outer electron shell, which is also full. It has 8, so it's an electron configuration of 2,8,8 minus. So both ions now have full outer shells. They're happy. And the sodium ions have the formula Na+, and the chloride ions have the formula Cl-. In the dot cross diagram, you'll need to show one sodium ion and one chloride ion, with one ion's electrons shown as dots and the other as crosses. And again, you only have to show the valence electrons, not the other electrons involved. So a more complex example is calcium chloride. So in this example, a calcium atom gives one electron to one chlorine atom and the other electron to a second chlorine atom, which you can see here by these two red dots. The result is a calcium ion of 2,8,8,2 plus and two chloride ions, both of 2,8,8 minus and 2,8,8 minus. They both have, all three now have full outer shells. And the calcium ion has a formula of Ca2 plus and the chloride ions have a formula of Cl minus. Just like in the previous example, you'll have to show the two chloride ions because two chloride ions are needed to balance the charge on the calcium ion.
We have previously learned about the formation of ions. Now we will learn about ionic bonds. Ions, as you already know, are formed from the loss or gain of electrons. Electrons, however, do not suddenly appear or disappear. They are, in fact, transferred from one atom to another. Let's look at sodium chloride as an example. Sodium loses one electron to form a sodium ion. The electron is not lost, but transferred to chlorine to form a chloride ion. So we have a sodium ion and a chloride ion. They are oppositely charged ions and will be electrostatically attracted to one another much like how opposite poles of a magnet are attracted to one another. This electrostatic attraction is an ionic bond. Sodium chloride is an ionic compound because it is held intact by ionic bonds. The same thing happens with magnesium and oxygen. Why don't you grab a piece of paper and a pencil and draw the resulting ionic compound, magnesium oxide? Please pause the lesson and resume when you are done. Magnesium transfers its 2 valence electrons to oxygen, forming a magnesium ion and an oxide ion. The resulting ions are electrostatically attracted to one another, forming an ionic bond. Did you get this right? Did you remember to include the charges on the ion? Now, let's look at calcium and chlorine. Calcium loses 2 electrons to form a calcium ion. One of these electrons is transferred to a chlorine atom, and another is transferred to another chlorine atom, forming 2 chloride ions. The calcium ion is electrostatically attracted to the 2 chloride ions because the opposite charges must fully balance each other out. In all 3 examples, the resulting ionic compounds have an overall neutral charge because all charges are fully balanced out. In summary, an ionic bond is defined as the electrostatic attraction between oppositely charged ions. When an ionic compound is formed, the charges must be balanced so that the resulting ionic compound has an overall neutral charge.
So finally, let's look at the structure of these ionic compounds. They actually exist in something called a crystal lattice. Okay, so the example of sodium and sodium chloride is that you have 6 sodium ions attracted to 6 chloride ions. Okay, so it's a 6:6 ratio, which we break down to a common factor of 1:1. That's why sodium chloride has the formula of NaCl. And ionic substances like sodium chloride form giant ionic lattices containing oppositely charged ions. They have high melting and boiling points and conduct electricity only when melted or dissolved. They don't conduct when they are solid. Now, what is the reason for this? Well, the high melting and boiling points are because ionic bonds, the electrostatic attraction between the ions, is very strong. So it takes a lot of energy to break these ionic bonds. So ionic compounds, therefore, have the high melting and boiling points. They are only conductive when liquid, because ions are charged particles, but ionic compounds can only conduct if the ions are free to move. If they're all stuck in a crystal lattice, like we see here in the diagram, they can't move, so they're not going to be able to conduct. Okay, just like electrons are needed to move in a wire for electricity to travel, such as the same for ions. And ionic compounds do not conduct electricity when they're solid, only when they're dissolved in water or melted because of this reason. Okay.
So far, we have looked at ionic compounds as single entities. Ionic compounds actually exist as large 3D structures known as a giant ionic lattices. In this lesson, we will learn about, and you got it, these giant ionic lattice structures. When we talk about sodium chloride, there aren't actually any individual sodium chloride molecules. Instead, the sodium and chloride ions are arranged in a regular repeating 3D pattern known as a giant ionic lattice. Let's now have a look at the giant ionic lattice of sodium chloride. We know that sodium and chloride ions are electrostatically attracted to one another. Because of this, you will see that the ions are arranged so that the sodium ions are always next to the chloride ions. This arrangement is seen in all directions of the 3D structure. The electrostatic attractions in a lattice structure are very strong. Let's think about it. Each sodium ion is held in place by the electrostatic attraction of 6 neighboring chloride ions in all possible 3D directions. And similarly, each chloride ion is held in place by the electrostatic attraction of 6 sodium ions, also in all possible 3D directions. Since this lattice structure is so strong, it explains some key properties of ionic compounds. Ionic compounds have very high melting points. This is because a lot of energy is required to overcome the strong electrostatic attractions holding the 3D lattice structure in place. Ionic compounds are also very brittle. This means that they break rather easily into small pieces. A ceramic flower vase is also brittle. If knocked over, chances are it will break into small pieces. But why are ionic compounds brittle? When a force is applied to the 3D lattice structure, it will disrupt the regular repeating pattern of sodium and chloride ions. So the sodium ions are forced to be next to other sodium ions, and the same is seen with chloride ions. Like charges repel one another, and this repulsion essentially breaks the lattice structure. In summary, ionic compounds exist as giant ionic lattices, not as single molecules. The giant ionic lattice is a regular repeating 3D pattern of alternating positive and negative ions. The electrostatic attractions holding the structure intact are very strong, and this accounts for the fact that ionic compounds have very high melting points and are brittle.